Hello everyone, this is Manas, your friend and tutor. And guys, welcome to another session on mechanics of solids. Today, we are going to take up three different cases. To be very specific, I'm going to talk about volumetric strain and its calculation for a uniaxial load, biaxial load, that is load applied in two directions, and also for a triaxial load, that is when you apply load along x, y and z directions. What happens? How much volumetric strain is encountered? All these things and much more coming up in today's session. But first of all, let us just do a quick recap of all that we had learned in the previous lecture. And if you haven't seen my previous two lectures, well, the link to them can be found in the description down below. Go ahead and check it out. It's going to be a very eye-opening session for you in context of mechanics of solids. So the first thing is, all these are elastic constants. Why are they termed as elastic constants? Because in all the cases, okay, when you apply the load, there is going to be some deformation. Okay, there is deformation along the direction of load. And then there is deformation in case of shear modulus also, something of this sort, right? If you apply a tangential force, then this point shifts over here slightly, say from B to B dash, right? So different kind of deformation takes place under different kinds of loadings. And here also in bulk modulus, what happens is, if you have a block like this, then it has been applied a force in all the directions. In such a case, the entire volume of the block would change, and that's how bulk modulus is calculated. That is the normal stress with respect to the volumetric strain EV, and this EV is what today's session is all about, and calculation of EV under different cases. So let's quickly get started with this. And the first thing that we are going to study is what exactly is volumetric strain. So let's see that. Okay, so by definition, volumetric strain is defined as the change in volume with respect to the original volume, right? Now, how can volumetric strain be mathematically represented? First of all, it is represented by EV, and EV is nothing but the change in volume with respect to the original volume. So this is how you can write this volumetric strain mathematically. But do we have an expression? Yes, we do have an expression for volumetric strain. It says total volumetric strain is a sum of linear strain along x, along y and along z directions. But how can we reach to this conclusion? That is something that we are going to discuss right now. So let's take up a very general case. Let's say we've got a cube over here. Let me quickly make this, okay, like this. And let's say this is L, that's B, and what about this? Let's call this as H. Now, let's say we are pulling this cube from all the directions, from X, from Y and from Z directions. Let's say that this right here is the Z direction, this right here is the X direction, and this right here is the Y direction. What will happen? There is going to be obviously some change in L, some change in B, and some change along the H direction, right? So the original dimensions, let's say the original dimensions are X, not X, but let me just write this L, B, H, and the dimensions which have changed, the changed dimensions or the increased dimensions, okay, new dimensions, let's say, they are represented by L plus delta L, B plus delta B, and also H plus delta H. Okay, now if I were to calculate the change in volume, what I need to do is new volume corresponding to the new dimension minus old volume corresponding to the old dimension or the original dimension, and that's what we are going to do right now. Let's see how all of this works out. Okay, I need to change my pen. So let's see this quickly. Right, change in volume, EV is equal to change in volume. What is the new volume? Let's say that the new volume corresponding to these dimensions be represented by V2 and the original volume be represented by V1. So in that case, the delta V upon V can be expressed as V2 minus V1 with respect to original. Again, this is going to be V1, right? Now, watch this carefully. V2 minus V1. Okay, so what's V2? V2 is this, right? So how do you express the volume? Length multiplied by breadth multiplied by height. So this can essentially be written as, right? This is the new volume minus original volume, that is length multiplied by breadth multiplied by height divided by, again, that's going to be the original volume, that is LBH. Now guys, this task is a bit painstaking. What you need to do is you need to do the multiplication of all these three inside bracket terms. Let's see how that works out, and final expression that we are going to get will be this, which states that the net volumetric strain is a sum of linear strain along x, y and z directions. Let's see how we can reach this conclusion. Here we go. So first of all, I am multiplying these two brackets. Now what we'll do, we'll try to multiply these two brackets. Let's see how everything works out. And all of this, right, divided by LBH. Now just take a look. These two are going to cancel out, right? And apart from this, you need to take a look at those terms which are extremely small, very small, and those quantities are to be neglected. Let me tell you what they are. So if you've got a quantity delta, let's say delta x in itself is a very small quantity, and that small quantity when multiplied by another quantity which is extremely small, that in fact can be neglected. And this is the policy which I am going to apply over here. So there is only one small quantity, so that has to be accepted. Here you can clearly see there are two small quantities in multiplication. That means the final product is going to be very, very small. So this can be neglected. Again, this can be taken. There is only one small quantity. Here also, if you watch, this is also again turning out a very small quantity. Why? Because there are two deltas. Anything else? Yes, this is also very small quantity. So the ones which I am circling are extremely small quantities, and I am going to be neglecting them. Okay, this also, again, there are three deltas. So let's neglect this also. And now let us write the remaining stuff. So the remaining stuff is something like this. Right? Delta L dot B dot H, then there is LB dot L dot B dot delta H, and all of this divided by what? LBH. Now just take a look at this. When you divide this by this, okay, so this denominator has to be divided individually by this, and by this. So the stuff remaining is going to be del L by L, and BH will cancel. From here delta B will remain, LHN will cancel, and from in this expression delta H upon H will remain, and LB and LB will cancel out. So ultimately the final stuff that we are going to get is something of this sort: delta L upon L plus delta B over B plus delta H over H, which in fact is nothing but the linear strain along X direction, linear strain along Y, and this is the linear strain along Z direction. Okay, this L is along X direction, so change in length, right? Change in length with respect to original length will give you the strain along X, strain along Y, and strain along Z direction. So in totality, what you can write is, here in the LHS you see EV ultimately will work out as EX plus EY plus EZ, and this is why we say that the total volumetric strain in case of a cuboid, let's say, is equal to the sum of individual strains along X, Y and Z directions. That's the entire idea, right? Now let's take this session forward. Now let us try to develop a relationship between the load applied and the deflection or deformation, right? It's something like this. Let's say, first of all, let me write the topic's name. Just take a look at this case. Let's say we've got a cuboid like this, okay, and something like this. What happens when you apply load to it? Let's say we are applying a compressive load. The name of the load is given by P, right? What will happen? It is going to get compressed somewhere along this direction. Let's say this initially was the length L. Now there is going to be some change in length along this direction. Let's say this is delta L. Now if I were to tell you, try to connect stress and strain with Young's modulus. So Young's modulus essentially can be written as E is equal to stress upon strain, right? And this is the linear strain I am talking about. Stress is nothing but load over area, and that's the cross-sectional area that I am interested in, okay, P upon A. And this is nothing but the change in length over original length. And if I were to tell you there is a relationship directly which connects P, A, L and E, it's like this. Delta L will travel here, delta L will be equal to what? This L will go upwards, PL upon this A, E. And please copy paste this relationship inside your mind, because this is something which I'm going to be using very much, right, in the upcoming videos on numericals also and in the upcoming derivations also. So this is going to be very helpful for us. Now again, let's kick off. Now that you have understood what exactly volumetric strain is, we are going to see the first case. That is the case where only one load is applied, say along X direction. What happens? How can you exactly find the value of volumetric strain in that case? Let's see how all of that works out. So it would be very important, first of all, to just pause the video and note all of this down, right? Okay. Let's say this is the X direction. This over here represents the Y direction, and this right here represents the Z direction or Z axis. Let's call this as L. Let's say this is B, and let's say this is thickness T. Okay, you can write it as height H also. What we'll try to do is we'll try to apply a load, and that is going to happen only along one direction. Let's say that we will apply load along the X direction. Let us name the load as Px, and the corresponding stress which it is going to generate, let's say that is sigma x. Okay, from here also Px. I'm not putting it up, don't worry. Now we wish to calculate the volumetric strain along this case. So volumetric strain in this case, EV will be equal to what? Sum of linear strain along X, along Y and along Z. Fine, perfect. So the first thing that we'll try to immediately do is to calculate the linear strain. Now the strain along the direction of load is linear strain, and the strain developing perpendicular to the direction of load, that is lateral strain. And this is something that we had studied in Poisson's ratio. Where is Poisson's ratio? Yes, here it is. Okay, and there is a very important relationship. Poisson's ratio mu is equal to lateral strain. We just write it over here. Lateral strain with respect to the linear strain, and there is always a minus sign. Remember this. If there is an increase in direction, if there is an increase in dimension along X, so there is going to be a decrease in dimension along Y, and so on. This is very mutual. Okay, so we wish to calculate the value of linear strain along the X direction. How can that be done? It's very easy. So the linear strain, first of all, E is equal to what? E is equal to strain, not this way. Instead of writing E, let me just write Young's modulus E can be written as what? Stress over strain. Very easy. Okay, so here I am representing the strain by small e. So along X, so in Ex can essentially be written as sigma X over E, isn't it? So Ex, direct linear strain, Ex will be equal to what? Sigma X upon E. Done. That is going to be your equation number 1. You've got Ex, no problem. Can you get the value of Ey? Ey. What is the change in dimension along y direction? Now here comes in the picture of Poisson's ratio. Just watch this carefully. If you apply a load along the x direction, okay, this L is going to definitely increase for sure. But what about this B? Just think about this, guys. If this L is going to increase, then simultaneously this dimension B is going to reduce and this thickness T is also going to reduce. What is this strain? This is lateral strain. If there is linear strain along L or along x direction, there is lateral strain along B, along T. If there is a load applied along x axis, due to that there is linear strain along x axis, but due to that load there is lateral strain along z direction and lateral strain along y direction. Okay, now let us just try to connect lateral strain with linear strain. Just remember this: lateral strain is equal to mu times linear strain. Just try to remember this relationship, linear strain. Okay, lateral strain is equal to mu times linear strain, and it would be better if you can just put a negative sign also. Lateral strain is negative of mu times linear strain. Okay, so let me just write this up. So there is no force acting along the y direction, so there is not going to be any linear strain. The only strain developed along y direction is the lateral strain, and this lateral strain is due to what? Due to this sigma x. Due to this sigma x, there is lateral strain along y direction due to sigma x. So how can you express this? You can express it in this manner, which is also equal to what? Minus of, again this is minus of what? Mu linear strain, the linear strain, okay, that is sigma x upon E. So this is how you can express lateral strain. In the same manner, there is Ez. So Ez is, again this is same, lateral strain due to sigma x. Again, if it is a lateral strain, which is equal to negative times of mu into linear strain, mu times of linear strain, that is this sigma x over E. Now you've got all the three values of strain, 1, 2 and 3. Now we wish to calculate volumetric strain, EV. EV is equal to what? 1 plus 2 plus 3. When you add all of these up, what will happen? Let's see, sigma x by E, sigma x by E and sigma x by B. All of it can be taken as common. So let me just write sigma x over E, and the stuff remaining inside is going to be 1 minus mu minus mu. So this is going to be, guys, 1 minus 2 mu. 1 minus 2 mu. So this is going to be a very important relationship, especially in case of uniaxial loads and the corresponding calculation of volumetric strain. Very, very important. So please pause the video and note this down. Okay, now let's take this session forward and let's try to do the same for a biaxial loading. Again, let's have the same object. Here also let's have a cuboid, but the thing is, here the load applied or the application of load will be along two directions. Okay, and let's say like this. So that's along y. No, we initially did this as z axis. This is x axis, and this right here is your y axis. This is length and this is breadth. Let's say this is thickness t. We really don't need that. Anyway, so there are going to be axial pulls from two directions, along x and along y. Let me just show you. Along x, it's going to be something like this. Okay, this is going to be load along x is px and the corresponding stress is going to be sigma x. In the same manner, the load applied along y direction is like this. this is going to be what? Py, and the corresponding stress generated is going to be sigma y. Now let's try to analyze this. Okay, what we want? We want the volumetric strain. Volumetric strain is given by EV is a sum of strain along x, strain along y, strain along the z direction. So individually we will be calculating Ex, Ey and Ez. Let's see. So first of all, let's work out Ex. Okay. So the load acting along x direction is Px, and because of Px there is going to be linear strain due to sigma x or Px, whatever you can say. So Ex, you can write this linear strain due to Ex. Okay, what else? Along the x direction, what else is happening? Now the nature of this force is such, the nature of this stress sigma x is such that it will try to extend or it will try to lengthen this length L. Okay, it is trying to increase this length L. Is there any other force or is there any other stretch which is trying to decrease this length L? Yes, sigma y. So what will happen is plus lateral strain. Okay, so along this x direction, this is actually perpendicular to this y direction. Now this force, due to this force, there is going to be this stress, and the nature of this stress is such that it will try to decrease this length, sort of, you can say, lateral strain due to sigma y. Now stuff is going to be very easy. So linear strain due to sigma x is going to be sigma x upon E. And you know how do you need to express lateral strain? Lateral strain is negative of Poisson's ratio multiplied by the linear strain. Linear strain, that is because of sigma y. So sigma y over E. That's it. In the same manner, guys, what we can do is we can also calculate the value of Ey. Ey will be equal to what? Linear strain due to sigma y. Okay, so there is going to be a change in length, that is change in dimension B along this y direction because of this sigma y. That's exactly what we have done. Plus this B also changes because of whom? Because of this sigma x. Now this is lateral case, so let me just write this lateral strain due to, along the y direction there is some lateral strain due to, well, sigma x. Now it's very easy. So Ey is going to be equal to what? Sigma y over E minus again mu times of, okay, strain due to x, what? Sigma x over E. Again remember, what is lateral strain? Lateral strain happens in a direction perpendicular to that of applied load. Okay. So if you are initially analyzing x, so the load applied along x direction, just think about this. This is the load applied along x direction. There is linear strain along x, but there is going to be lateral strain along y, and also z also. We'll be analyzing that also. When you talk about the load applied along y direction, there is going to be linear strain along y direction, but at the same time there is going to be lateral strain along the x direction. Okay, so that's it. And final call, Ez. So if you watch this, there is absolutely no force acting along the z direction, no force. So whatever strain is going to develop along this z direction, along this dimension t, it is purely because of lateral strains due to sigma y and due to sigma x. It's very simple. So this is a summation of lateral strain due to sigma x and sigma y. So how can you write this? Negative of mu sigma x over E, again negative of mu sigma y over E. Done. Now we need to do the entire summation. EV is equal to what? EV is a sum of sigma x, Ex, Ey and Ez. So what we can do is you can actually add all of them up. Sigma x over E, and there is sigma x over E, that minus mu sigma x over E. So what I can do is, first of all, let me just write this sigma x over E. Okay, sigma x over E. sigma x over e, sigma x over e, sigma x over e. So if we just try to take a common, this is going to be 1 minus mu and minus mu. So this is going to become 1 minus 2 times of mu. Okay, anything else? Now let's talk about this sigma y over e. Sigma y over e, let's take that as common, plus sigma y over e. Now if you try to work out, this is 1, okay, minus mu, all of them have been covered. 1 minus mu, so 1 minus 2 mu. There you go. Now what you can do is you can take these two as common. 1 minus 2 mu can be taken as common. So this is going to become 1 minus 2 times of mu, and this is going to be sigma x plus sigma y upon E. So this is the final expression for the volumetric strain of a cuboid having dimensions L, B, T when it is subjected to load along X and load along Y direction. And this is exactly how you can get the volumetric strains. All these results are going to be extremely important because in the next video we will be developing relationships or expressions which connect Young's modulus with modulus of rigidity, Young's modulus with bulk modulus, and there is going to be one more relationship which sort of connects all the three elastic constants along with this Poisson's ratio mu, right? So these were the two cases, initial two cases. Now let us take this session forward and let's talk about case number 3. This is again going to be very, very beautiful, and if you have understood these two cases, case number 3, triaxial loading, is going to be very, very easy for you. Let's see how that works out. Biaxial, let me just this much will do the job, right? Okay, and what else? Okay, let me just modify this. Okay, load along X, load along Y, and now in case number 3 we have a triaxial loading case. Triaxial loading case, case number 3. So along with X and Y there is going to be a force acting along the Z direction also, like this, along the Z direction, right? Let's call this as PZ and sigma Z. Okay, let me just erase these tick marks. Now let's try to analyze this. Ex, we are trying to find out the total strain along X direction. So there is linear strain along X direction due to this sigma x upon E. But along X direction there is going to be some lateral strain also due to sigma Z and due to sigma Y. So plus lateral strain due to sigma Y, and this is going to be sigma Z. So in that case this is going to be sigma x over E minus mu times of sigma Y over E minus again mu times of sigma Z over E. It's that simple. In the same way, linear strain along Y, let's calculate the total linear strain, total amount of strain along Y. That is linear strain due to sigma Y, fine. But there is going to be lateral strain also along this direction because of sigma x and sigma Z. So here we will have sigma x and sigma Z. So this is going to be minus of sigma Z over E. It's that simple. Now Ez, let me just rub this up, plus linear strain due to what? Sigma Z, isn't it? And here there is going to be sigma Z over E. So Ez basically is equal to, this is the linear strain along Z and this is the lateral strain along Z. This is also is the lateral strain along Z. Let me reiterate. Total strain along X is the linear strain along X minus the lateral strain along X, lateral strain along X. This lateral strain was because of sigma Y, this lateral strain was because of sigma Z. Here also this is the total strain along the Y direction, right? This is the linear strain along Y. This is the lateral strain along Y due to sigma x. This is the lateral strain along Y due to sigma Z. That's the entire idea. And when you have to find the total value of the volumetric strain, you take a sum, Ex plus Ey plus Ez. When you do that, what will happen? Let me tell you. Sigma x over E can be taken as common, minus mu and minus mu. So sigma x over E. Let me just write it over here. Sigma x over E 1 minus, this is going to become 2 mu. In the same manner, you will have sigma y over E 1 minus 2 mu, and also plus sigma z over E. This is going to be 1 minus 2 mu. It's that simple. And finally, you can see these three are common terms. So what you can essentially do is you can write finally EV is equal to 1 minus 2 mu, and this is going to be sigma x plus sigma y plus sigma z, all of that divided by E. So this is the final expression for a cuboid having dimensions L, B and T, which is being pulled from all the direction, from X, from Y and from Z. And this will form the foundation for trying to develop a relationship between bulk modulus and Young's modulus. This result is something that I'll be using up directly, right? EV is equal to 1 minus 2 mu, sigma and all of this stuff. So now that we have discussed all the three cases of volumetric strain, there is something else which I had to tell you. Let me just check. Okay, there is also a volumetric strain of a circular bar, which I am supposed to discuss. Let's just finish this. Let's consider a circular bar. Yeah. And there is a load applied. Let's call this as load P, right? This is the circular bar. And that circular bar is having a length of, let's say, L, and is having a diameter. If this is the side view, then the diameter is D, let's say. Okay. Now, what needs to be done is, when you apply such a load, how much is the volumetric strain? Can you go ahead and calculate that? Well, that can be done. Again, the fundamental is going to be remaining same. Volumetric strain EV is nothing but the change in volume with respect to the original volume. If you watch carefully, the dimensions are such, how much? L, this is the length of the bar, you can say, and the cross section is how much? The cross section rather has a diameter D. So what we can essentially do is, V, let's say, can be written as pi by 4 D square into L, D square L. This is the original volume. And let's say initially all the dimensions were D and L, but after applying the load, let's say the dimensions change. D becomes D plus delta D, and let's say L becomes L plus delta L. In that case, the new volume, let's say this original volume is V1, the new volume, let's say, is V2. The new volume V2 will become, is equal to what? Pi by 4, this, that is D plus delta D square into L plus delta L. So this is exactly how you can express it. Okay, so delta V will be equal to what? V2 minus V1, and this is original volume V. Original volume is what? V1. Now let's plug in all these values into this expression and let's see how it works. These are all very small changes, and these changes are such that on removal of this load P, this entire circular bar will regain its original shape and size, right? So we are working within the elastic range. Okay, let's see. Let me use rather a blue color. Okay, so this is going to work out as V2 minus V1. So pi by 4 can be taken as common, and the remaining stuff, let me write it inside. Pi by 4, let's take it as common. What about the remaining stuff? D plus delta D square, L plus delta L. Okay, minus V2 minus V1. Again, pi by 4 already has been taken as common. The stuff remaining inside is D square L. All of this divided by original volume. What it is? Pi by 4 D square L. That is D square dot L. So pi by 4 and pi by 4 will cancel out. What we need to do is we need to solve this bracket, and this is going to be really very tiresome. Let's do this. all, I need to open this bracket. A square plus B square plus 2AB. Now, let me multiply this with this, then this, with this, and so on. Let's do this. Now guys, we need to take care of the terms which are extremely small. So there is only single delta, so this will be accepted. There is no delta, this also will be accepted, right? This is double delta. You can see there is a square with delta. So the square of a very small quantity, what you can do is, let me circle this, because this is what we are going to neglect. So the terms that I am circling are the ones which have to be neglected. Again, there is already a delta over here, then delta square. So multiplication of 3 deltas is going to turn out into a very smaller quantity, so that can be neglected. There is only one delta here, accepted, and there are 2 deltas here. This again has to be neglected. Now the stuff becomes very easy. The only thing that we need to do is, please watch this, d square L and d square L will cancel out. The stuff that is going to remain inside, d square delta L, let me just write all of this, d square delta L and 2d delta d and L, and yeah, that's it, whole divided by d square L. Okay, now if you just try to work out, just do the division, d square and d square will cancel out, delta L upon delta L, delta L over delta simple L, plus 2 times of dl will cancel out. Am I right? Yes. Only the stuff only remaining will be 1d will be remaining in the bottom. This is going to be delta d over d. So what is this? This is linear strain. What is this? 2 times of. You can call this as lateral strain. Okay. You can call it as lateral strain, or you can also call it as diametral strain. That is the strain acting along the diameter. Right? So 2 times of, I am putting this as diameter. So essentially what you can write is volumetric strain in case of a circular bar which is subjected to an axial load along this length L, EV is actually a sum of linear strain plus 2 times of diametral strain. This is exactly how you can achieve this expression. So guys, that was all for today, and the most important expression was this one, triaxial case, and that is something that I will be taking up in the next video, because in the next video we'll sort of try to develop relationships between E and C, E and K, and then a final relationship connecting all the 3 elastic constants. Again, that was all for today. I'll see you again in the next video. Until then, take care, have a nice day, keep learning. Thanks for watching.